A modern artificial intelligence can synthesize legal arguments, write functional code, and pass medical exams in seconds. Yet, despite all of this immense processing power, its visual processing can be completely shattered by a single, microscopic, invisible mathematical flaw. In 2013, researchers like Christian Segedi uncovered a structural vulnerability in machine learning known as adversarial examples. They proved that you could take a neural network trained to recognize everyday objects and deceive it into confidently misclassifying a weapon as a harmless household item. This visualization demonstrates Gaussian noise. By overlaying a specifically calculated layer of static onto an image, an attacker can physically warp the data the AI processes, completely changing its interpretation without altering the image to the human eye. This vulnerability triggered an ongoing arms race between cybersecurity researchers trying to patch these models and attackers developing more sophisticated illusions. The foundational fragility of artificial intelligence was located in its literal eyesight. Fast forward to modern large language models. Engineers largely solved the problem of direct logic manipulation through rigorous text filtering. Companies invested massive computational power and millions of dollars into reinforcement learning from human feedback, or RLHF, to harden the text inputs. Think of RLHF as a highly restrictive checkpoint. If a user types a malicious prompt, the text guardrail intercepts the packet and instantly rejects it. But the landscape shifted with the deployment of vision language models, or VLMs, which accept both text and images simultaneously. AI safety protocols were built entirely around the AI's ears, its text processing. Developers assumed the visual inputs, the eyes, would passively inherit those same strict safety alignments. This imbalance created a compounding security debt. The industry built an incredibly secure text processor, but attached a visual processor that bypassed the established checks. Millions of hours of RLHF successfully bolted the front door of the AI, while leaving an unmonitored architectural side door wide open. To see exactly how this side door operates, we have to look inside the internal architecture of open-source VLMs like Lava and QuenVL. These systems use a dual encoder design, physically split into two modules. The first is the vision transformer, compressing raw pixels into abstract visual tokens. The second is the language decoder, the brain. If you send a harmful text command here, the RLHF firewall immediately blocks it. The vulnerability lies in the synchronization between these modules, the cross-modal gap. Visual tokens generated internally by the VIT get priority routing. A payload originating here routes completely around the text firewall, injecting directly into the LLM's logic center. By the time the LLM receives these tokens, it automatically categorizes them as a pre-cleared, safe image analysis task. The VLM lacks the physical architecture to detect malicious intent, as long as the instruction arrives disguised as a visual payload. The consequence of this routing flaw becomes explicit when we look at the AI semantic embedding place. This 3D scatterplot shows how an AI plots queries on a multidimensional map. It groups meanings to isolate danger. The green dots represent safe queries, tightly clustered far away from the red dots, which represent harmful requests. When interacting through plain text, the AI's semantic radar maintains strict isolation between toxic and safe concepts. Visual injection attacks explicitly target and manipulate the spatial coordinates of these queries. Fed through the image channel, a harmful query mathematically forces the distinct clusters to collapse into an overlapping mass. In this blended state, the underlying LLM's threat detection can no longer differentiate between the distinct points. This visual injection completely corrupts the mathematical framework that the AI uses to differentiate between safe and catastrophic requests. Researchers from Tsinghua University engineered a specific algorithm to weaponize this data blending. They call it FigStep. FigStep operates as a black box attack executed in 3 strict phases, beginning with strategic paraphrasing. First, the attacker lowers the query's perplexity score. They take a harsh, violent command and rewrite it to sound like a sterile educational outline. A request for weapons manufacturing instructions is translated into a generic request for chemical synthesis steps. Once the text is softened, the attack moves to phase 2, typographic injection. The attacker converts the paraphrased text into a high-contrast digital screenshot, formatting it as an excerpt from a technical document. This physical conversion migrates the attack payload entirely out of the highly guarded text lane and sets it up for the unprotected visual lane. Finally, the attacker initiates Phase 3, the incitement trigger. They pair the typographic image with a heavily structured text prompt. They might ask the AI to fill in the missing descriptions for the empty 123 list shown in the image. This exploits a core feature, its helpfulness bias. The AI becomes so hyper-focused on completing the structural pattern that it overrides semantic filters. FigStep weaponizes the primary directives to be helpful and complete patterns against its safety protocols. To patch this vulnerability, the industry deployed an established tool, optical character recognition, or OCR filters. This diagram illustrates an OCR preprocessing filter. It physically reads and flags banned words in an image, intercepting them before the VLM can ingest the file. OCR blocked the initial typographic attacks, but the filter relies entirely on analyzing an image in a linear, predictable sequence. In response, the researchers developed an adversarial escalation specifically designed to blind the OCR scan, known as FigStep-Pro. The evasion mechanic relies on a process called sub-figure concatenation. The attacker takes the typographic image and physically shatters it into dozens of isolated, non-sequential grid tiles, breaking the words into abstract shapes. When the OCR scans this payload, it evaluates each fragmented tile individually. It reads them as meaningless semantic noise and clears the entire batch as safe. But once the tiles bypass the filter and enter the central AI node, the VLM's native spatial attention map automatically reassembles the fragments back into their original, readable structure. The exact spatial awareness architecture designed to give vision models their advanced capabilities is precisely the tool weaponized to smuggle the payload past the defenses. To quantify the effectiveness of this mechanic, researchers tested it against the SafeBench dataset. This data dashboard tracks the results across 6 distinct open-source models. As the tests concluded, FigStep achieved an 82.5% average attack success rate. The models generated enthusiastic, step-by-step instructions for tasks explicitly forbidden by their core safety guidelines. Had these exact same requests been submitted through a standard text prompt, the system would have rejected them in milliseconds. The success of FigStep demonstrates that the current standard of unimodal safety alignment is obsolete. This research highlights the necessity of cross-modal safety parity. Security engineers have to build systems where the visual encoders are trained to natively recognize the exact same mathematical threat models as the text decoders. Until visual security catches up to text security, every advanced multimodal AI system operates as an impenetrable fortress with an open back window.